The next speaker in this session is Robert Jonsson from Nordita, the Nordic Institute for Theoretical Physics at Stockholm University. Title: Entanglement Harvesting in 3+1 Dimensional Schwarzschild Spacetime.
Thank you, Jorma, for this introduction, and thank you also for stressing already why we are happy or excited about this project. And thank you at this point, of course, to the organizers for putting together this conference at such short timescales. This is work we are doing together with João Caribe and Marc Casals in Rio de Janeiro and Dublin and Leipzig University, in fact, and with Achim and Eduardo, who you probably all now know. And yes, it's another entanglement harvesting talk, and why we're excited about it is that we are here looking at the Schwarzschild spacetime in 3+1 dimensions. So this should be the real physical black hole, or at least the first textbook Schwarz example of a black hole that we look at entanglement harvesting here. Maybe that's more for the connoisseurs, but then for everybody, one other takeaway message should be that we think we have observed here something which nicely connects to the question that Ericsson just raised about what role causal connection plays when we try to harvest, to extract entanglement from the quantum field. Because in the end, of course, entanglement harvesting is being driven by the question, how is space-time curvature, space-time geometry, and the entanglement properties of the field, how are these two connected? And what can we say about them? So I will make use of the fact that I was just preceded by many entanglement harvesting talks in this session, and also on Monday we already had an entanglement harvesting talk. In fact, in a Schwarzschild in a black hole space-time by Laura, and just really briefly remind us here of the things that maybe are important for this overview of our work. We use point-like two-level Unruh detectors. We will use a Gaussian switching function, and we will in fact put Alice and Bob as static observers at equal radial coordinate in the Schwarzschild black hole spacetime. Only their switch on times will shift a little, or can be different. And we will couple them to a massless Klein-Gordon field. So it's the very standard ingredients that we use here. We start them off both in the ground state, the product of ground state in both detectors. Then we do the coupling. We use time-dependent perturbation theory to arrive at the final state, which will have, once you trace out the field, this 4x4 density matrix. And here we know, right, that we can use negativity as a measure for entanglement in this final state. And we had this formula just before. This is just to remind us that what determines whether the two detectors end up entangled is a competition between certain correlating terms that occur in the density matrix. It's this M term here, this off-diagonal term. And it competes against the local noise that each detector experiences, independent of whether the other detector is even there or not. This L term here wouldn't change because of that. So it's a competition between the correlation and the noise, which determines whether the detectors end up entangled. And what are these M and L terms? Very well, they are the usual sort of Fourier type integrals with all those prefactors over the Wightman function. So there's the Wightman function of the field, which knows how strong the local noises that the detectors experience, and which knows whether the detectors are going to end up entangled, because it knows how strong they will be correlated in the end. And this is, again, basically a recap of what Ericsson just said. For the purpose here, when we want to distinguish whether this entanglement that we find in our detectors was actually extracted as a pre-existing entanglement in the field, or maybe whether it was generated while the detectors were both interacting with the same medium. For this consideration, it helps to split up the Wightman function, or also known as the two-point function of the field, into its real and its imaginary part, or its anti-commutator or commutator. There are different names for that. If you look at the, I probably should have put an I here. Well, if you look at the right-hand side where we have the commutator of the field, we know that this part of the Wightman function is state independent. It factors out of here, and it's the same for all possible quantum states. We know that it behaves strictly causal, so it vanishes at space-like separation. And we know that it's the one when you look at signaling, or actually just the communication channel between detectors. This is the part of the Wightman function which carries information, carries signals from Alice to Bob. And on the left-hand side, we would have the real part, which is given by the anti-commutator of the field. And this, of course, depends on the particular quantum state you choose for the field. We know it to be non-vanishing at space-like parts, space-like separations. So we also know that that's the part, for example, where you can extract space-like entanglement from the field. And Ericsson has given us the argument that this is the part where we would expect the pre-existing field entanglement to show up. What do these two parts of the Wightman function look in 3+1 dimensional Minkowski space? Well, we know that there the 2-point function is strictly supported only on the light cone, where it's also singular. And the commutative part goes like a Dirac delta of here the Schwarzschild function, which is negative inside the light cone, positive outside of the light cone. So the commutator part goes like a Dirac delta and with some prefactors, and the anti-commutator part goes basically at this principal value 1 over sigma distribution. And Ericsson has just showed us in their result, which shows that, well, as soon as detectors are causally connected, so Bob is somehow on or inside of the causal light cone of Alice, that then the extracted entanglement actually is dominated by contributions from the commutator. So we would be skeptical, or rather say, well, this is entanglement surely generated by the fact that Alice and Bob have just been interacting with the same degrees of freedom of the field. And this, of course, raises the question whether this observation is a consequence of causal connection. Is it always the case that, when these detectors are in causal contact, that they're actually just generating the entanglement, not really extracting pre-existing entanglement? And how can we find out? Now, it will not come as a surprise to you that I will be suggesting Schwarzschild, 3+1 dimensional Schwarzschild spacetime, as an interesting spacetime to look at this question. And why is that? Well, I'm going to try to play this video, and I hope you see it in decent quality, where we remind ourselves that in Schwarzschild spacetime, the light cone has a much more interesting structure. Right here, of course, we see that initially it's the light cone emanating from this red point. Well, first it forms a circle which soon gets distorted as the light cone, as part of the light cone, approaches the black hole here in the middle with radius 2m. And then I'll play it again. So here it looks almost like a circle. Now it starts to getting distorted. And then as it wraps around the black hole, we have this caustic forming on the other side, where the light cone meets itself and penetrates itself just to wrap around the black hole yet another time, meet again at the original point, or at this gamma equals 0 angle, and so on and so on. So we can expect two things here to happen. One is, of course, that at these caustics, I should go on. At these caustics, we have a lensing effect, right? You can revolve this whole picture on the y-axis. So there maybe entanglement harvesting also gets enhanced or possible again at larger distances. And the other thing that's interesting that's happening here is that the Wightman function in Schwarzschild spacetime has an interesting fourfold singularity structure. So every time the light cone goes through a caustic, it shifts its singularity structure. Here, for the first part, the one that hasn't seen itself, it's the usual singularity structure. But then as soon as the light cone has gone through one caustic down here, the singularity structure has shifted. Now the commutator behaves like a 1 over sigma principal value, while the anti-commutator gives you a delta. And this goes on and on and on. But then, what we learned from Ericsson was that, okay, it's the delta terms that tend to dominate entanglement harvesting. So this could very well mean that if we do entanglement harvesting with Bob being located here, the delta term, we would expect that one to dominate the extraction of the extracted entanglement. Thus, it would in fact be the anti-commutator of the field, which we would associate to the pre-existing entanglement in the field, which now dominates the extraction or the harvesting process. So to answer this question, what do we need to do? We need to calculate the full Wightman function. We want to do this for Boulware, Hartle-Hawking, and the Unruh states. And we then need to put this, of course, into these convoluted exponential integrals entering L and M. So to be able to calculate this, what you typically would have to do is, call someone like Tjoa and Mark. They're the experts, the clear experts here for all the numerical work and the knowledge of how the Wightman functions and the different Green's function of these Hartle-Hawking states on black hole spacetimes behave. So, get in touch with them if you have more questions, read their papers, and start with collaborations. And a big thank you to the two for that they are and keep collaborating with us.
You have 2 minutes.
Excellent. Then let's just look at what we actually found. I hope this plays in a good enough quality. Now here, what is happening, I'll stop the video at a certain point that we see in, we know from Minkowski spacetime, we have L sitting at the red point, and then different bobs. This is an axis gamma, so it takes you once around this black circle at radius 6m. And it's the bobs, like the time delay between the switching is such that those bobs which sit here where the light cone intersects with the black circle, that they are exactly aligned with Alice's switching. So we see that here, when Bob catches all the light rays, entanglement harvesting is possible, and that it's dominated, as we would expect, by the commutator, because the two are causally related. Then as time goes on, we have an effect that down here, the signal is too weak, and in fact, this red line, which is L, the noise time term, overcomes the correlations. So at this distances, no entanglement harvesting is possible at all. And that holds true up until here, where we see that now back at the caustic, where the light cone again merges with itself or meets itself, the correlations get stronger, they overcome the noise level, and we see entanglement harvesting happening. Still, though, it's dominated by the anti-commutator. So still, we would call this entanglement harvesting by signaling or by communication. But now, once the caustic has passed, we see that now in this region, we still have entanglement extraction. The M term overcomes the noise, but it is dominated by the yellow anti-commutator line. So here we have the same terms dominating the entanglement extraction as we have when we look at the extraction of space-like entanglement in Minkowski spacetime.
You are pushing into your question time.
Then let me just tell you, the following. This was just a recap of what I just told you. We looked at this for the 3 different states. There are no big differences, and the differences come about because the noise term is different in the 3 states. So the correlation terms tend to be the same. There are some differences in the noise, strength of noise, and thus there are some differences in the extractive entanglement, but overall the qualitative behavior is the same. And well, these were the 3 points I tried to get across to you. We looked at the different vacua. We see some lensing at the caustics, and we see that also after the caustic we see that entanglement harvesting is dominated by the anti-commutator, which we would associate to pre-existing field entanglement. And I'd like to thank you and leave you with a slide maybe on top with all the references. Stay tuned for our works. I think in the next couple of months, we would have it out. Thank you.
Thank you very much. Now, I'm going to postpone my questions to the joint question time. A very quick question here, if there is one.
Well, I got one.
Oh, is it? Okay, I think Rob was first.
Oh, Keith had one. I've asked. Let Keith do it.
Okay, Keith, quickly.
Yes, great talk. I'm going to have to pick you and Casal's brains later. How hard is it to calculate the Wightman using these methods near the horizon?
That's really a question we should ask Mark and Joao, because I mean, they did it, and we would just ask them question. We have, I mean, that also depends on what's close to the horizon, right? They get, I mean, to me, they get impressively close to the horizon. Then I don't know how near to the horizon you need it. And I would invite you, we should ask this question to them in the Slack if they are around, or also anytime by email, of course.
I will. Thank you.
I'm sorry that I basically have no answer to this. No reason.
Okay, I will.
Thank you again.
I'm just a bit, I think it went a bit fast and I missed it. So when you run that different, the video frames as the communication part changes in the role, right? Can you explain a little bit what does different frames as the video moves on, what is changing?
Oh, sorry. Yeah, my timing was off there. The maybe I can bring it up as well, if that's okay. It was here, and we can look a little at it while it runs. There is a time increasing here, right? And basically, that's the time shift between Alice and in coordinate time. Let's go for coordinate time between where Alice and Bob have their detector switched on. So they use the same shape of Gaussian switching function with a certain width, but one of them, I mean, Alice switches on at 0 or peaked around 0, and Bob switches on later and later. And the matching is that well, if we are here, then we see at this time difference, coordinate time difference between the peak, we see that the left plot is indicating that within this time, the light cone will have expanded into this form.
Oh, okay.
And therefore, so light that has emanated from Alice at time 0 has after t equal 8.5 m made its way to here. And therefore, if Bob sits exactly at this angular separation, which is what we see on the right, meaning here, or the second is there, then of course he catches all the light rays, so he has the best chance to get entangled.
Okay, so in this case, you are moving the videos in units of m. So your switching function is how many units of m? I can't quite see.
Yeah, no, this resolution turned out too bad here. Oh, maybe I can go like this. So what is increasing is basically time. I mean, in the left plot, right? Because you see how the light cone expands. And,
yeah, okay, I get it.
On the right hand, what is changing, basically the same time that is playing in the video here, is also the time difference between the peaks of the two Gaussian switching functions.
Great, thank you.
I can drop a link to this presentation in the Slack if people want to play around with the videos.
Could I abuse my position and ask Robert? So the key, so one key phenomenon here is that the light cones, they cross. Suppose you were in flat space, but you made one of your spatial coordinates a circle. Do you think you'd see a similar phenomenon?
I think we had this discussion just in the last meeting that you can recreate certain of these effects you could probably do with mirrors, that you have this shifting of the singularity structure, yes. Circles, I don't know. That would be something for Mark, right? I mean, if you make one of them periodic, I don't know, like we should ask that in Slack to Mark. I do know that with certain mirror arrangements, one should be able to have this shifting of the singularity structure too.
That would need much less numerical power.
Yeah, certainly.